This is Dharamvi sir here. So today we are going to start, or I can say that we are going to continue with chapter 9 of grade 12 maths, which is differential equations. And in this video we are going to learn how to find the solution of a differential equation whose variables are separable. That is, we can separate x and y. Okay, such differential equations are called variable separable. Clear? So let's start. So what is a differential equation with variable separable? So if we have a differential equation dy upon dx in the function of x and y, and somehow we can separate x to one side and y to other side along with dx and dy. So y and dy should be on one side, x and dx should be on other side. Then such differential equations are called differential equations with variable separable. As you can see that we have dy upon dx. As the function of xy, and if we can somehow take hy dy and gx dx to other sides, okay, so such will be called a differential equation with variable separables. So let's start the exercise. Very simple. So let's start exercise 9.4, and the question 1 is find the differential equation. For the differential equation, find the general solution. We have dy upon dx equals to 1 minus cos x upon 1 plus cos x. So it is very simple. All the x are on one side, just we have to cross multiply the dx. So cross multiplying dx, we get dy is equal to 1 minus cos x upon 1 plus cos x into dx. Now we have to integrate. We have learned enough of integration. So integral of dy will be equal to integral of, now 1 minus cos x is 2 sin square x by 2, and 1 plus cos x is 2 cos square x by 2 dx. So simplifying, we get y, integral of dy is y, integral tan square x by 2, and integral of tan square is not very easy, so we have to convert it in the form of sec square x by 2 minus 1. So integrating sec square x by 2 minus 1, we get tan x by 2 upon half minus x plus c. Okay, so the solution for the given differential equation, general solution, because we have some constant over here. We have learned about general solution and particular solution. So the general solution will be y is equal to 2 tan x by 2 minus x plus constant of integral c. Clear? Moving to question 4, for the differential equation, find the general solution. And the question is sec square x tan y dx plus sec square y tan x dx equals to 0. Now dividing both sides by tan x tan y, we get sec square x upon tan x dx plus sec square y upon tan y dy. Now we have to separate the variables, x on one side and x together and y together. So we have already separated the variables. So integrating both sides, we get integral sec square x upon tan x dx plus integral sec square y upon tan y dy equals to log c. For the constant we are taking log c. So you can simply say that integral sec square x upon tan x dx will be equal to log tan x plus log tan y equals to log c, because we know this property that integral f dash x upon fx dx equals to log fx. So we are getting log tan x into tan y equals to log c, and then tan x tan y will be equal to plus minus c. We are using c, capital C, for the plus minus c because constant can be anything. So the general solution for the given differential equation is tan x tan y equals to plus minus c or c. Clear? Moving to question 5. For the differential equation, find the general solution. We have the differential equation as e power x plus e power minus x dy minus e power x minus e power minus x dx equals to 0. So writing this, separating the variables, we have dy equals to e power x minus e power minus x upon e power x plus e power x dx. So integrating both sides, we get integral of dy is equal to integral e power x minus e power x minus e power minus x upon e power x plus e power minus x dx. So we can see that this is in the form of integral f dash x upon fx dx, which is equal to log fx. We get y is equal to log e power x plus e power minus x plus constant of integral c, which is the required general solution because the constant is here. Clear? Moving to question 7. For the differential equation, find the general solution. We have y log y dx minus x dy equals to 0. So first we have to separate the variables. So taking x and y, we get minus x dy equal to minus y log y dx, and separating the variables we will get dy upon y log y is equal to dx upon x. So integrating both sides we get integral dy upon y log y is equal to integral dx upon x. So for the left hand side we have taken log y equals to t, so we get 1 upon y dt upon dy is equal to dy upon y equals to dt. So equation 1 becomes integral dt upon t equals to integral dx upon x, which can be written as log t is equal to log x plus log c. Why log c? Because we have log t and log c, so we are taking the constant as log for the simplification of calculation. So this log x log c will become log x into c, so t becomes xc, so t is equal to xc. So we are getting log y is equal to xc, or in place of c we can take simply a. So the general solution becomes y is equal to e power ax. Clear? So pause and note down the solution. Next we have question 10. For the differential equation, find the general solution. And we have e power x tan y dx plus 1 minus e power x x square y dy equals to 0. Now the given equation is e power x tan y dx plus 1 minus e power x x square y dy equals to 0. So dividing both sides by 1 minus e power x tan y, we get e power x upon 1 minus e power x dx equals to 6 square y upon tan y dy equals to 0. That is, we are separating the variables. So integrating both sides, we get integral e power x upon 1 minus x square dx plus integral 6 square y upon tan y dy equals to c. So multiplying by minus, we get minus integral minus e power x upon 1 minus e power x, and the integral of 6 square y will be log tan y plus c. So simplifying, we are getting log tan y upon 1 minus e power x equals to log c. So remove log, we get tan y upon 1 minus e power x equals to c. So the general solution will be equal to tan y equals to c into 1 minus e power x, which is the required solution. Clear? So pause and note down the solution. Moving to question 13. For the differential equation, find a particular solution. So we have to remove the constant, satisfying the given condition. We have cos dy upon dx equals to a. So cos dy upon dx equals to a, so we are writing dy upon dx as cos inverse a, or dy becomes cos inverse a into dx. So integrating both sides, we get integral of dy equals to integral of cos inverse a into dx. And since cos inverse a is constant, we are getting y is equal to cos inverse a into x plus c. Now we have to find the particular solution, and it is given that y is equal to 2 when x equals to 0. So putting this, we get the value of c as 1. So putting c equals to 1 in the equation 1, we get y is equal to x cos inverse a plus 1. And simplifying, we will get our required particular solution as cos y minus 1 upon x equals to a. Clear? So pause and note down the solution. Moving to question 14. For the differential equation, find a particular solution satisfying the given condition, and the equation is dy upon dx equals to y tan x when y is equal to 1 and x equals to 0. So we have the differential equation dy upon dx equals to y tan x. So separating the variables, we get dy upon y equals to tan x dx. So integrating both sides, we are getting integral 1 upon y dy equals to integral tan x dx. So integrating, we are getting log y is equal to log sec x plus log c. Why log c? Because both are log. So on simplifying, we are getting y is equal to c into sec x. Now it is given that when y is equal to 1, x is equal to 0. So putting this value, we get the value of c as equal to 1. So putting c equals to 1 in the given equation, we are getting the particular solution as y is equal to sec x. Clear? So pause and note down the solution. Moving to question 16. For the differential equation xy into dy upon dx equals to x plus 2 y plus 2, find the solution passing through 1 and minus 1. So we have the given differential equation as xy dy upon dx into x plus 2 y plus 2. So separating the variables, we are getting y upon y plus 2 dy equals to x plus y upon x dx. So integrating both sides, we get integral y upon y plus 2 dy equals to integral x plus 2 upon x dx. So writing this as integral y plus 2 upon y plus 2 minus 2 upon y plus 2 dy is equal to integral 1 plus 2 upon x dx. So integrating, we are getting y minus 2 log y plus 2 equals to x plus 2 into log x plus c. So using the properties of log, we are getting y minus x equals to log y plus 2 whole square plus log x square c, or y minus x is equal to log y plus 2 whole square into x square plus c. Now it is given that it is passing through 1 1. So putting x equals to 1 and y is equal to minus 1, we get the value of c as minus 2. So putting c equals to minus 2 in equation 1, we are getting the particular solution as y minus x plus 2 is equal to log into y plus 2 whole square into x square. So this is our required solution. Clear? So pause and note down. Moving to question 18. At any point xy of a curve, the slope of the tangent is twice the slope of the line segment joining the point of contact to the point minus 4 minus 3. Find the equation of the curve given that it passes through minus 2 1. So we have to find the equation of curve. So it is given that we have at the point pxy a tangent passing through xy. Okay. So we have to find the equation of the curve that passes through minus 2 1. Now we have the question, slope of the tangent is equal to 2 times of the slope of the line joining P, that is xy, and the point A, that is minus 4 minus 3. So we are getting dy upon dx equals to 2 into this one by using the formula for slope. That slope is equal to y2 minus y1 upon x2 minus x1. So on simplifying, we are getting dy upon dx equals to 2y plus 3 upon x plus 4. So separating the variables, we are getting dy upon y plus 3 is equal to 2 upon x plus 4 dx. So integrating both sides, we have integral 1 upon y plus 3 dy equals to 2 integral 1 upon x plus 4 dx. So it is very simple, log. So we get log y plus 3 is equal to 2 log x plus 4 plus log c. Clear? So applying the properties of log, we are getting y plus 3 equals to c into x plus 4 whole square. Now it is given that it is passing through the point minus 2 1. The curve is passing through the point minus 2 1. So putting the value of x equals to minus 2 and y is equal to 1, we get the value of c as 1. Clear? So using the value of c as 1, we get y plus 3 is equal to x plus 4 whole square, or simplifying, we'll get x plus 4 whole square equals to y plus 3. So this will be the required equation of the curve. Clear? So pause and note down the solution. Moving to question 20. In a bank, principal increases continuously at the rate of r% per year. Find the value of r if rupees 100 double itself in 10 years. And we have the value of log 2 base equals to 0.6931. Now we have the principal p, time t years. Now it is given that the rate of increase of principal is equal to r% of the principal. Clear? That is rate of change of principal. So dp upon dt is equal to r% of p. So separating the variable, we get dp upon p is equal to r upon 100 into dt. So integrating, it becomes log p is equal to r upon 100 t plus constant c. Now we have to find the value of c. It is given that initial principal was 100. It is given. So initially time is equal to 0 and principal is equal to 100. So putting this value in equation 1, we get log 100 equals to c. Okay. Now putting log 100 equals to c in equation 1, we get log p is equal to r upon 100 t plus log 100. So applying the properties of log, we are getting log p upon 100 equals to r upon 100 into t. Now it is given that the principal double itself. The principal become 2 times of 100, so 200. And it is also given we have to find t is equal to 100 when the value of r. So log, in place of t we are using 200, so log 200 upon 100 equals to r upon 100 into t. We got t is equal to 10. So we are getting log 2 is equal to r upon 10. And the value of log t was given. So using the value of log 2 as 0.6931, we get the value of r as 6.931%. Clear? So pause and note down the solution. Moving to question 22. In a culture, the bacteria count is 1 lakh. The number is increased by 10% in 2 hours. In how many hours will the count reach 2 lakh if the rate of growth of bacteria is proportional to the number present? Now let x be the bacteria present at the time t hours. Okay. Now according to the given, the rate of growth is proportional to the number of bacteria present. It means that dx is proportional to x. Now dx upon dt equals to kx. So separating the variables, we are getting dx upon x equals to k into dt, and integrating both sides, we have integral 1 upon x dx equals to k integral dt. So we get log x equals to kt plus c. Now we have to find the value of c. So initially the bacteria count, suppose x is given to be 1 lakh, initially time is equal to 0. So putting these values, we get c is equal to log x0, where x0 is equal to 1 lakh. Okay, so putting the value of c in equation 1, we get log x upon x0 equals to kt. Now we have to find the value of k. Again, it is given that number of bacteria increased by 10% in 2 hours. So increasing bacteria in 2 hours equals to 10% of initial, that is 10,000. So x, the amount of bacteria at t is equal to 2 is equal to what? 1 lakh plus 10,000, that is 1 lakh 10,000, which is equal to x1. So putting x equals to x1 in equation 2 and t is equal to 2. So we get log x1 upon x0 equals to 2k. That is k is equal to half log x1 upon x0. Now putting the values of x1 and x0, we have k is equal to half log 11 upon 10. So putting the value of k in equation 2, we get log x upon x0 is equal to half log 11 upon 10 into t, and we have x equals to 2 lakh. So putting all these value, we will get log 2 is equal to half log 11 upon 10 t, and cross multiplying we have 2 log t is equal to this one, or t is equal to 2 log 2 upon log 11 upon 10 hours.